Hey guys, how's it going? So this video is going to be video 2 in the Circuits 1 series. We're going to be talking about power calculations, series and parallel circuits, and passive sign convention. The objectives of this video are going to be to determine if a component is in series or parallel, calculate power, and use passive sign convention to show if a component is a source or if it's a load. Series elements. Elements in series share the same current but experience different voltages, and loops connect these elements in series together. We can see this from the drawing on the top right. The easiest way to determine if a group of elements is in series is to put your pencil down on the paper and draw a line following the circuit. If there's only one path for you to go, they are in series. If you get to a point where you have multiple paths that you can take, they now become in parallel with each other. So you can see if we start at this point on the top left and we draw a line straight over, we get to our next node. There's only one path for it to go, straight down. Same thing with the next node and the next node. There's no other path that we can take. So therefore these four objects, C, B, E, and D, are all in series with each other. In our water example, all series elements share the same water flow, but at each element, they experience a drop in pressure. As you can see in the picture on the bottom right, the water source is acting as our voltage, and the pipe going down is carrying all of our current. The current's flow rate is the same through all of the elements, but the pressure will drop a little bit after each resistor, but the same amount of water flows through even at the end. So remember, for series elements, they share the exact same current, but they have different voltages. Parallel is like last time in the series, where loops connected elements, but this time nodes connect elements. Elements in parallel share the same voltage, but they experience different current values. In the example to the top right, we can put our pencil down and draw a loop, but when we hit a point where they can branch off, these elements now become in parallel. So we can see if we start at the top right and we draw our line over, we hit this node right here, and we can either go up or we can go down. So these elements are now in parallel with each other. They combine back after these elements, and we draw our line again, but then now we hit another node where we have paths for current flow. So these elements now become in parallel with each other. However, if you're looking at just these individual branches, resistor 4 and resistor 5 are in parallel with each other because right here between them, there is no alternate path for the current to go. All the current that enters resistor 4 must leave resistor 5. So resistor 4 and resistor 5 are in series, but resistor 6 is in parallel with these two resistors. The same thing is true for the one on the right. Resistors 2 and 3 are in series because the same current flows through both of them, but resistor 2 and 3 are in parallel with resistor 1 because when you get to this top point, current can split as necessary, and it will recombine down here, and the current will flow back to the source. In the water example, all parallel elements share the same water pressure, but they experience less flow rate. So you can once again see that the tank on the top is acting as our voltage source. Instead of there being one path for current to flow, there are multiple paths for current to flow. You can see that the water pressure felt on all 6 of the elements is the exact same, but the flow rate is going to be different depending on the size of the pipe. So remember, elements in parallel share voltage, but they have different currents going through them based on their resistance. Let's go over some examples of series or parallel. So for figure 1, we're given resistor 1, 2, and 3. So if we draw our line straight through resistor 1, we hit this node right here, and now we have two paths that current can flow, either straight down through resistor 2, or it can go over through resistor 3. That means that resistor 2 is in parallel with resistor 3. However, once you leave resistor 2 and 3, they combine again and they go back down the wire. So overall, we can say that resistor 1 is in series with resistor 2 and 3. However, resistors 2 and 3 are in parallel with each other. For example 2, we see that resistor 1 and 2 are in series with each other, but 1 and 2 combined are in parallel with resistor 3 because as current comes down, it can either go straight down through resistor 1 and resistor 2, or it can go straight down through resistor 3. But then once again, they recombine, so we can say that resistor 1 and 2 is in parallel with resistor 3, and that resistor 1 is directly in series with resistor 2. Continuing these examples for figure 3, this one's drawn a little different, but the same principle still applies by putting your pencil down and seeing where it takes you. So if we start at the top and we come down, we hit a point. Current can either go over or it can go down. So that means that resistor 1 is in parallel with something. So let's see, as we keep going straight down, we go through resistor 2, and as we turn, there's no other path right here for current to go. All of it must go through 3, and then it hits this node. The current going through resistor 1 will also meet up at this node, and they will combine back together. So this shows us that resistor 2 is in series with resistor 3, but resistor 2 and 3 together are in parallel with resistor 1. For figure 4, we can see that as current comes in, it can either go down through resistor 1 and 2, or it can go over through resistor 3 and 4. So that means that these are in parallel with each other, but as you go straight down, there's no path for current to go right here. So resistor 1 and resistor 2 are in series with each other, and the same is true for resistor 3 and resistor 4. But because they recombine at the end, we say that resistor 1 and 2 are in parallel with 3 and 4. So just to recap, resistor 1 and 2 are in series with each other, and the same is true for 3 and 4. They're in series with each other. But if you look at them overall, resistors 1 and 2 are in parallel with resistors 3 and 4. And for our last two examples, we see figure 5. We can see that current comes down. It either goes through resistor 1 or it goes through resistor 3. So that means that resistor 1 and 3 are in parallel with each other. And then as it comes down, there's nothing here. There's nothing here except a wire. So what this really means is that this just acts as a single point. So we can redraw this if we want to look like this. So this drawing right here is the exact same as the given on the right. So we have resistor 1, resistor 3, resistor 2, and resistor 4. So as we have a different path for current coming through 1 and 3, that means that 1 and 3 are in parallel with each other. As it recombines and it goes through this node, this means that 2 and 4 are also in parallel with each other. But overall, resistors 1 and 3 are in series with resistors 2 and 4. So if you were to combine resistors 1 and 3 and combine resistors 2 and 4, it would give you a circuit that looked like this. And we'll talk about combining resistors later, but we can see that this overall resistance is in parallel with each other, but it's in series with this overall resistance. And lastly, figure 6 is similar to one on the last page where we have current coming in. It can go one of two directions. So resistor 3 and resistor 2 and 1 are in parallel with each other, but resistor 2 is in series with resistor 1. Power calculations. Remember the mnemonic from last time? Power is easy as pi. P equals I times E. Let's do this example where we're calculating the power of a resistor that drops 10 volts and has 10 amps going through it. So remembering the equation, power is equal to current times voltage. We can see that 10 volts times 10 amps will give us our power, which in this case is 100 watts. In the second example, let's calculate the power of a resistor that drops 5 volts and has negative 5 amps going through it. So power is equal to 4 volts times negative 5 amps, which equals negative 20 watts. We see here that we have a negative power. Let's discuss what that means. Power. Let's talk about what it means if we have negative or positive value for power. A positive power means that each element in question is using power. Resistors will always use power. You can think about positive power as energy being burned off. A heat sink and a heat source are other good ways to imagine it. A heat source puts heat into a system, a computer CPU, for example, and a heat sink pulls that power out of the system. In that example, the CPU cooler removes the heat from the system. And in the electrical world, your source would be like a current source or a voltage source, and that would usually be a negative value because that's putting power into the system. Your resistors and other loads would be your sinks or burning off that power. Negative power means that power is being supplied to the system. Current and voltage sources, as explained before, are usually examples of power sources. However, they can be sources or loads depending on whether the power value is positive or negative. That's why we use passive sign convention. But remember, resistors will always have positive power, meaning they will always burn off power. A resistor will never supply energy to the circuit. Passive sign convention. Many people get nervous when they hear passive sign convention mentioned. However, all it does is tell us whether we need a negative sign in front of our power equation. We usually imagine current as flowing from positive to negative, but this is not always true. Current flow is just a matter of perspective. Imagine you're staring in a river and it's flowing in your view from right to left. If you walk on the other side of the river and look back at it, it's now flowing left to right. But overall, the water is still flowing from one point to another. Your point of view has just changed because your perspective has changed. Another way to look at the current flowing out of an object is it's the same as the negative current flowing into the object. So let's give an example. In this one, we're given that current is 10 amps. Now look for the arrow showing the direction assumed with this. In this example, that means that the current is 10 amps flowing in the direction of the arrow. In this next example, we are given that the current is equal to negative 10 amps. Because the current is negative, you can flip the given arrow so that the negative 10 amps leaving the positive terminal is the same as 10 amps flowing into the positive terminal. This isn't required. However, it is all mathematically the same. This is where we can use passive sign convention to help. We'll now see how that works in more detail in the next few examples. To determine an object's power, remember earlier that power equals current times voltage. Next, we're going to locate the direction of current flow. Then we're going to locate the current's value. And if the current is entering the positive side of an object, we're going to put a plus in front of the I times Z equation. Similarly, if it's entering the negative side, we're going to put a negative in front. Next, write out the current value for the I and write the voltage value for the V. Multiply these values out, and the answer is the sign and the numerical value. Let's do some examples with passive sign convention. In example 1, we are given that current is 10 amps and the voltage is 5 volts. Looking at the given drawing, you can see by the current arrow that the current is entering the positive side. So using our current times voltage equation and the plus from it entering the positive terminal, we can see that power equals plus times 10 amps times 10 volts, which gives us plus 50 watts. The plus obviously just goes away, but this means that the power is positive. Therefore, the component is a load. If you remember from the previous slide, a positive power means it's a load and the negative sign means it's a source. In example 2, we can see that we have a current of 10 amps and a voltage of 5 volts. If you look at where the current flows into the object, we can see it's leaving the negative terminal, so we must enter a negative in front of the power equation. So this gives us that power is equal to negative times 10 amps times 5 volts, which is negative 50 watts. The power is negative, so therefore the component is a source. In example 3, once again, we have that current is 10 amps and our voltage is 5 volts. However, if you look at the current direction, we can see it's leaving the positive terminal. It's generally easier to talk about current entering an object than it is trying to imagine it leaving an object. So I like to move the arrow to the entrance side. You can do this by the reasoning that if something leaves an object and it has no other path for it to go inside of that object than out, the same amount of stuff that leaves the object must enter. So instead of us having the I leaving the positive terminal, we can rewrite that as the I entering the negative terminal. So when we do our power equation, we use the passive sign convention and we put our negative in front of the equation. So we have negative times 10 amps times 5 volts is equal to negative 50 watts. Remember, the negative means that the component is a source. In example 4, we have negative 10 amps for current and 5 volts for voltage. Once again, we see that current is leaving the negative terminal. However, negative current just means that the arrow is backwards. So you have two options. You can either change the arrow and make the current positive, or because it's leaving, you can have it enter the positive node instead of leaving the negative node. I'm going to leave the current value as negative, and I'm just going to move the arrow so it enters the positive. Just like last time, the same amount of stuff must leave that enters. So the current enters the positive node. So we put a plus in front of the equation. Our current is negative 10 amps, and our voltage is 5 volts, which gives us negative 50 watts. So once again, our component is a source. That's it for this video, guys. Leave a like and subscribe if you haven't already, and feel free to reach out or leave a comment with any questions. Thanks.